So, welcome everyone to this online conference on geometric representation theory at the Institute. It's a real pleasure to have Zhiwei Yun as our first speaker, who will be talking about Theta intertwining sheaves. So thank you, Zhiwei.
Thank you very much, and it's a great pleasure to speak in this conference. I'm going to speak on some joint work in progress with Shangar Gurevich. So this is, in a very in rough terms, we are trying to geometrize the theta correspondence over a finite field. So I will spend some time explaining the representation theoretic motivation, reviewing the theta correspondence over a finite field, following the ideas of Roger Hall and other people. And then I will motivate from a geometric perspective by recalling Lustig's notion of character sheaves, how they are constructed. So our the main result I'm going to talk about is sort of is a mixture. It combines the theta correspondence with character sheaves, and I'll try to explain what that produces. These are the so-called theta intertwining sheaves. And if I have time, I'll list some properties of these sheaves and some examples. Okay. So let me start with a quick review of the Wei representation and theta correspondence. So first, Wei representation over a finite field. The setup is to fix a symplectic vector space of finite dimension over a finite field. Always assume the characteristic of K is not 2. Attached to this vector space, we consider the Heisenberg group, Heisenberg extension. So it's a 2-step nilpotent group. Center is K, is a copy of this finite field, and quotient is V, and the commutator pairing of two liftings of 2 elements from V, the commutator lies in the center, and it's given by the symplectic form. If we fix a non-trivial additive character into some coefficient field, so I always consider QL bar, then there's a unique irreducible representation of the Heisenberg group with central character psi. So restriction to this central K is psi. So let's denote this by HV. So this is a representation whose isomorphism class is uniquely determined by this additive character. So concretely, you can realize it by the so-called Schrodinger model. If we take any splitting of L into 2 Lagrangian subspaces, and then we can realize HV as functions on, let's say, the second one. Okay, so there are various models for this representation. Once every time you pick a Lagrangian splitting, you get a model, and the symplectic group So this I just view it as a finite group, the FQ points of this algebraic symplectic group. Since it preserves, since it acts on the Heisenberg group, it will preserve the isomorphism class of this representation. So it acts on the projectivization of this of the vector space HV. It's a result of Girardin. He constructs an explicit lifting to an actual representation. Instead of a projective representation. Okay, so this is the Wei representation. Let's denote it by omega psi. It depends on, yeah, so this, everything here depends on this additive character. So maybe I write its dependence. So this is the Wei, also called oscillator representation of the symplectic group. Now, let's come to Hall's correspondence. So Roger Hall proposes to consider a pair of subgroups inside this symplectic group that are called dual reductive pairs. So they're basically commutator of each other. There are three basic examples of such pairs. First is the symplectic orthogonal pair. You take a symplectic vector space V1 and you take orthogonal space V2 and you consider their respective automorphism groups. And for V, we just take the tensor product, okay, and it carries a symplectic form. This way we have a map from G1 times G2 to the symplectic group of the tensor product. They are a commutator of each other. So this will be the main example that we will talk about today. But there are two other kinds of irreducible reductive dual pairs. We can take a unitary group. So here V1 is over quadratic extension K prime over K. This is a Hermitian vector space. And then similarly take V2 equipped with a skew Hermitian form. And let V be the tensor product V1 and V2 over K prime. This carries, so you can trace down, take the product of two forms and you trace down to K. This carries a symplectic form. So G1, G2 is also an example of a dual reductive pair. And the third case, the third example is a split case of the second. We just take two vector spaces over K and let G1, G2 be GL of these vector spaces. So G1 times G2 maps to GL of L1 times L2. And this is viewed as a subgroup of the symplectic group. Well, so let V be actually maybe I prefer to write dualize L1. So I take V to be the direct sum of hom from L1 to L2 plus hom from L2 to L1. So this is a symplectic vector space equipped with the splitting into Lagrangians. And this GL is the GL of the first Lagrangian. This embedding is embedding as the Levy subgroup preserving the splitting. We will mostly consider the first case, which is in some sense the most complicated case. So once we have this pair G1, G2, we can take this oscillator representation and restrict to G1 times G2 and try to decompose it. So this is the theta correspondence proposed by Roger Hall. So this way, you can use this to define a map from the representation, the Grothendieck ring, Grothendieck group of representations of G1 to representations of G2. Well, if you have an irreducible representation of G1, you look at its multiplicity space. Well, so yeah, so just send it to hom. The multiplicity of rho in this oscillator representation as a representation of G2. So that at least defines a map on the level of Grothendieck groups. There has been a lot of work trying to explicitly describe this map theta. So let me just mention work of Aubert, Michel, Rouquier. They completely described how this theta works for unitary groups, and they made a conjecture about the orthogonal symplectic pair. And that conjecture has recently been proved by Shu-Yan Pan. So after their work, we do have an explicit description of the theta correspondence on the level of the representations. Okay, so but what I'm interested in is I want to look at the theta correspondence from a slightly different angle.
Zhiwei, can I just interrupt briefly? Shamgar just raised his hand about 5 minutes ago. I'm not sure if and also Jessica has a question. Are you able? Are people able to unmute themselves to ask a question? I guess or like if the question can wait till the end, maybe we can use the Q&A feature. Whereas if it's something that's actually inhibiting understanding now, then
so let me just open the chat.
Oh, so Jessica says she didn't mean to raise a hand.
Oh.
I just thought Shamgar might have had a comment relevant to what you're saying.
So Shamgar, do you want to say something?
Oh, Shamgar says it was a mistake. Okay, no problem.
Oh, okay.
Yeah.
Okay, these are two easy questions. All right.
While we're not asking questions, can I quickly ask? So this omega sub 5, this is a polynomial ring, but the actions aren't graded at all. Is that right?
You're asking about, oh, I see. So maybe I didn't make this clear. So this model, Schrodinger model, this really is viewed as a set. So all functions on this finite set They're not polynomial functions on a vector space.
Okay.
So everything here is over finite field. Just the
I see. Okay.
Yeah. Yeah. So the interesting feature or what makes this difficult than some other representations is that this model only allows you to see part of the symmetry. Because you've chosen a Lagrangian, it's easy to figure out how part of the symplectic group acts on this model. But to see how other elements act, you need to work with a different model. But eventually all these, this is really a single representation, but you can, to see the full symmetry, you have to use different models.
And is there an integral form of this representation that doesn't depend on the choice of Q?
Well, the dimension of the representation is a power of Q. So
I see that, but still, okay, fair enough.
Okay. So what I will look at are intertwining operators. So if we want to understand how this oscillator representation decomposes under G1 times G2, we can try to write down all the intertwining operators in their endomorphisms of omega psi under G1 times G2. This actually is a commutative ring, commutative algebra. This is a result of Maglan, Ross, Pouget. Namely, this decomposition into G1 times G2 modules, this is a multiplicity free. Okay, so for each irreducible representation of G1 times G2 that appears in the oscillator representation, we have a projector, canonical projector. So these form a basis for this endomorphism ring. And we can, this is a fairly canonical, maybe I call it an algebraic canonical basis. But they are not easy to write down. They're, you need to really understand all these representations to write down the projectors. So what we propose to find is a different set of, a different basis that deserves to be called geometric canonical basis.
So Zhiwei, sorry to interrupt again. So Shamgar says the statement about the commutativity is not true. I'm not sure, Shamgar, are you able to unmute yourself, or is that not possible? Okay, it doesn't seem to be possible. I have to allow you to unmute.
Okay, maybe I'll, I think he probably has something related, but not quite the same in mind. So I think this is true. Well, this is in the book by Maglan, Veneras, and Pouget.
Or in the Piatti case?
Sorry?
In the Piatti case, it's true, maybe.
No, this is also in the finite field case. And this is as representations of G1 times G2. So I'm saying a pair, rho 1, rho 2, appears, if it appears in the Theta correspondence, it only appears once. And for this statement, it's important to work with the full orthogonal group. The G2 is a full orthogonal rather than special orthogonal. Okay, so so the goal is to find another basis of geometric flavor So why do we expect such a basis to exist? Well, we can rewrite this ring a little bit. So far, it doesn't look very geometric because this omega psi is just some abstract representation, but its endomorphism just as a vector space, this can be canonically identified with functions on the Heisenberg group that has central, where the center acts by the additive character of psi. Okay. And by choosing just fixing the embedding of V, splitting Heisenberg group as K plus V, we can identify such functions just as functions on V. Okay, again, this is a functions on this finite set. V is just a finite, is a vector space over finite field. Okay, so the endomorphism ring, all linear endomorphisms of this oscillator representation has a canonical description as all functions on V. And this identification, so this is called a Weil transform. This allows us to identify intertwiners, G1 times G2 intertwining operators with G1 times G2 invariant functions on V. Okay, so this G1 times G2 just acts naturally on V, which is V1 tensor V2. So this looks a little bit more geometric. We are analyzing, a group acting on a vector space, and we want to find a basis for invariant functions of this action. So we may guess that maybe they are given by functions on constant functions on the orbit, or maybe these are not quite good, but you have to take Fourier transform of the spaces, etc. So that was kind of the starting point of this work. We were trying to guess what kind of functions on G1 times on V correspond to projectors to irreducible components of the value representation, and hopefully they are these functions actually come from sheaves on V, G1 times G2 equivariant sheaves. Okay, so at this point, there's it's clear how you should formulate the question geometrically. Namely, we want to find a collection of sheaves such that under the function to sheaf correspondence, they give a basis for this space, which is identified with intertwining operators on the oscillator representation. And we want to do this without using too much from representation theory, but just using mostly geometry. Guided by geometric considerations, we want to define such a collection of sheaves. Okay. So to arrive at the definition of such sheaves, let's review the theory of character sheaves, which will serve as a guiding example for our construction. So here, let's look at a group G is just any finite group of Lie type. And take its regular representation, G times G, acting on functions on G. We can also consider the intertwining operators of this representation as G times G representations. Okay, I just want to formulate things in a way similar to what we just discussed. So this is, it's easy to see this is just class functions on G. And it has two canonical bases. The algebraic canonical bases are given by irreducible characters. Again, to write down these irreducible characters, we have to know a lot about representations. Then there's a geometric canonical basis constructed by Lustig using character sheaves. And they viewed as conjugation invariant functions on G, they're called almost characters. So the relationship, the transition matrix between these two bases is almost diagonal. So you have, it's a block diagonal with the blocks of very small size, independent of Q. So they are close to each other, but the geometric canonical basis is constructed without knowing a priori about representation theory of G. So let's review Lustig's construction. Just in a unipotent character sheaf case. So the construction uses this diagram, the horocycle transform. Okay, so this divide, if I write this quotient in the form of a fraction, this means an adjoint action. Okay, so this is G mod G by conjugation. So Lustig defines a character sheaf to be anything you start with, anything you start here. So you can take a simple perverse sheaf supported on the closure of some Schubert cell, and then you pull and push. This way you get a semi-simple complex. So it's a direct sum of shifted simple perverse sheaves and simple summands are defined to be unipotent character sheaves. Okay, so you have to take all vary W in a while group. Okay, so this is the kind of construction that we are trying to mimic. So we can reformulate this in the following way. So what we start is functions on G mod B mod B. I can think of that as taking this regular representation as a G times G representation, and then I take a B times B invariance. Okay, so this is kind of the starting point. And using some kind of horocycle transformation, we arrive. So this horocycle transformation is basically the R step, pullback by R is just forget some symmetry, forget some invariance property. From by B invariant to conjugation B invariant. And this P push forward along P is just average. Okay, from B invariant to G invariant. Yeah, so you start with this b times b invariant vectors, and then you do you forget some invariance, and then you impose some more invariance. You arrive at a class function. So far it makes sense function theoretically, but until the last step of extracting sum ends, this operation doesn't make sense function theoretically, and that's the power of geometrization. It allows you to get more interesting objects. I mean, function theoretically, if you only start with b times b invariant functions, you're not gonna recover. You're not gonna get enough class functions to span the whole space. You're gonna miss those cuspidal representations. Okay, so yeah, so this is what we're trying to mimic, but the difficulty here is, as I said, this oscillator representation. Okay, so right here, what we're trying to mimic to kind of draw some analogy is between the oscillator representation with the action of G1 times G2 and the regular representation as a representation of G times G. But a crucial difference here is that this representation, regular representation, is really coming from a G times G action on some space, on some variety, by left and right translation. Okay, so it's in this case, it's more clear what to do geometrically. You have your variety here, and you know what it means to take b times b invariant vectors. It just means b times b invariant functions. Here, we don't have such a model that allows us to see the whole symmetry. So we have a Schrodinger model, which only allows us to see part of the symmetry. Yeah, so that's what makes this problem not a trivial generalization, not a trivial analogy of the theory of character sheaves. Any questions? Yeah, so I now come to part 3. I'll try to explain how we define this collection of sheaves. Yeah, so maybe I'll make this analogy a little bit further. So we want to, the output that we want to get would be a basis of this ring. Here, the analogous space is class functions. And this space on the left-hand side is geometric. So this is identified with G1 times G2 invariant functions on V. So we want to get a collection of sheaves here. On this side, we want to get a collection of sheaves, equivariant conjugation in the equivariant sheaves on G, and this is already achieved by Lustig. Here, we want to define a similar category or collection of simple perverse sheaves that we will denote by theta d G1 G2. Okay, this is to be defined. So that's the goal. Okay, so to define it, I will first have to break the symmetry to write the representation, oscillator representation using a Schrodinger model. So here, our V is V1 times V2 and choose a Lagrangian splitting. This gives us a Lagrangian splitting of the V just by tensoring with V2. Okay. These are Lagrangians in V, and this representation, underlying vector space of the Wave representation can be identified with functions on L prime. Now we want to start with B1 times B2 invariance. So that was inspired by the construction of character sheaves. Starting point should be Borel fixed vectors. So here, let's do similar things. So take B1, B2, Borel subgroups of G1 and G2. I take B1 to be compatible with to stabilize this this Lagrangian L1. So this is a Zhiwei parabolic of this form, and B1 is just upper triangular matrix in a symplectic group. So the action, so let me record the action of this part of the Borel. So this part is isomorphic to sim square of L1. This unipotent radical of this Zhiwei parabolic, and it acts on, so let's call this N1, NL1. It acts on this functions on L prime by multiplying with certain additive characters. By functions pulled back from the following map. So L prime is a tensor product. And remember, V2 is a quadratic space, carries a quadratic form. Let's apply the quadratic form to the V2 factor. That gives a map to sim square of V1 prime. Okay, so this is called moment map. And the action of this unipotent group, sim square of L1, is by multiplying with functions pulled back from pulled back along this moment map. Okay, so this group is dual to this sim square L1 prime. So each element in that group gives an additive character downstairs, and then you just pull it back. It's okay if you don't follow the detail, but then the upshot of this construction is that take this Wave representation. If you just look at invariant vectors under n of L1, the invariant under this red corner, these are exactly functions on the so-called moment cone. This is just the zero fiber of this moment map. It's a conical subset in this vector space L prime. And if you want to look at invariant functions under the whole Borel, this is identified with functions on this moment cone, invariant under, well, the B1 bar times B2. So here B1 bar is the part, is the image of B1 in its Levy quotient. So this part, this triangle is B1 bar. That acts on L1, hence on L prime. And the whole B2 acts on L prime as well. So this is just the natural geometric action on this cone. Okay, so this completes the geometrization of the starting point of our construction. So we should start with sheaves on this moment cone that are equivariant under B1 bar times B2. Okay, so this is a Borel fixed vector in the oscillator representation. Now to construct intertwining operators, we start with a pair of such, well, we have to double this, so let me write another. We want to start with a matrix coefficient, not just a vector. So we double the whole situation. We should think of this as taking a vector and a covector, and both of them are invariant under B1 times B2. And then we do some kind of Weil transform. So to arrive at B1 times B2 equivariant sheaves on V. And then we average. Okay, so this is analogous to the construction of character sheaves, except this, I need to explain a little bit what this Weil transform is, sheaf theoretically. So this Weil transform is function theoretically. This is going between functions on L and functions on L prime. Yeah, L prime times L prime. This is viewed as endomorphisms of functions on L prime given by kernel functions. So any linear endomorphism of this Schrodinger model is uniquely represented by some kernel function on the product. And Weil transform gives an isomorphism between these two vector spaces. And it is basically a partial Fourier transform because V is just L times L prime. If you start with L prime times L prime, you do, the second step is a Fourier transform, partial Fourier transform. First step, you do some linear transformation. It's some kind of Katie transformation, but it's very elementary. The second step is more interesting. The Fourier transform on the first factor, it turns L prime into L. But one feature of this thing, if you do it sheaf theoretically, is that it lands in sheaves that are B1 times B2 equivariant. Originally, we start with the smaller equivariance, apparently smaller because it's B1 bar square. But the difference is exactly this red square. Equivariance with respect to that part is already encoded in the condition that our functions or sheaves are supported on the moment cone. So yeah, so the result lands in B1 times B2 equivariant sheaves. Okay, so let me also remark that our starting point is very similar to G mod B mod B, in the sense that the action of B1 bar times B2 on the moment cone has only finitely many orbits. Like the Bruhat double cosets. Yeah, so we basically have finitely many simple inputs, okay, simple perverse sheaves to put here and follow these functors. We will get semi-simple complexes. So let's call this functor theta. Now we can define a theta intertwining sheaf is a simple perverse sheaf that appears in you applying the functor theta to some simple perverse sheaf, you know, the IC sheaf of some local system on some orbit in our in the moment cone. Yeah, so this is the definition of a theta intertwining sheaf, and we define the category to be just the full subcategory of G1 times G2 equivariant complexes on V generated by theta intertwining sheaves. So any questions at this point? One immediate question is that for the construction, I used a Lagrangian splitting. Right? So I chose L1 prime from the very beginning, and the whole construction depends on that choice. But the theorem ensures that this construction is canonical. So this these notions are independent of the splitting, Lagrangian splitting of V1 into the L1 plus L1 prime. So some remark about this construction. So what I did here is the analog of unipotent character sheaves. Yeah, I should say unipotent. So above are analogs of unipotent character sheaves. To get analogs of general character sheaves, we should start with some local systems. L1, L2 on T1, T2. So these are the quotient tori. Cartan quotients of B1 and B2. Well, this is also quotient of B1 bar. Start with rank 1 local systems on these tori. And then we just need to modify the starting point. So here, instead of looking at sheaves equivariant under B1 squared, B2 squared, we also put some, we just say equivariance against these local systems. Something like this. Okay. So that gives the general definition of character sheaf of a theta intertwining sheaves. That's one thing. Another remark is that we can also start by splitting V2. Let's say if V2 is even dimensional, even orthogonal group, then starting with the Lagrangian splitting for this orthogonal space, we can mimic this definition above and eventually get the same notion of theta intertwining sheaves. Okay. So let me maybe give some examples. So let's look at the example where V1 is arbitrary, the V2 is two-dimensional. Oh, by the way, so all this construction works over any, well, so it works in two kind of sheaf theoretic contexts. Either it's L-adic sheaves over a field of positive characteristic, or D modules in characteristic 0. Okay, and we can work with over FP bar, for example. So it's a completely geometric story. So for the example, I take V2 to be two-dimensional, and I'm allowed to extend my base field. So I assume this quadratic form is split. So I have I can choose a basis, basically choose a Lagrangian splitting. Right, so these are isotropic vectors. Now V is just V1, V1 E1 plus V1 E2. Okay, two copies of V1. So let me give the list of theta intertwining sheaves, unipotent theta intertwining sheaves in this case. Okay, so these are sheaves equivariant under SPV1 times OV2, acting naturally on this tensor product space. So first, we can take the constant sheaf on well, these two pieces. And take their direct sum. So I take their direct sum because I want to make it equivariant under the full orthogonal group, as opposed to just SO. Each piece will be equivariant under SOV2. This is one, and then let me. The next one is IC of D. So D is in V, parameterizes D is the subspace of subset of V. such that x is parallel to y. Okay, so V is just the V1 times V1, and I take a pair of parallel vectors, allowing one of them or both of them to be 0. So that's some singular subvariety in V. Its intersection cohomology complex is also a theta intertwining sheaf. Next one is I see of Q. Q is hypersurface where the pairing x and y is 0. So it's defined by a quadratic equation. Last one is we consider the map from V to A1, taking xy to the pairing, half of the pairing, using a symplectic form on V1. And then we take the pullback of Artin-Schreier psi plus Artin-Schreier psi bar. That's also a unipotent theta intertwining sheaf. Yeah, so this is the list in the simplest example when V2 is two-dimensional, is unipotent theta sheaves. Let me also just list a few features of these theta intertwining sheaves, and then I'll stop. Maybe, sorry, maybe I should actually stop here and just let people ask if they want to know more features. Yeah, I'll stop here.
Okay, so thank you, Zhiwei, for this beautiful talk. Perhaps we can so if someone has a question, they can raise their hand and then I'll unmute you and you can ask it. So George has a question.
Okay, so one question is, can you see this theta corresponds to take some unipotent caspitarization of symplectic groups, some other unipotent caspital of the orthogonal group. Can you see that in your picture?
I don't. Yeah, I can't. I mean, this. I don't have a clear statement how how sort of cuspidal character sheaves behave under this thing. There is a theory of the formalism parabolic induction. It has an analog in this situation, and also I did some example which shows in the simplest, the first case of a cuspidal character sheaf, it does show up. Well, I didn't say how to go from theta intertwining sheaves to character sheaves, but yeah, assuming that, then there is, yeah, in some examples at least, I can see this cuspidal character sheaves show up.
Oh, so another question is, do you know the relation between this theta character sheaves and the functions? So this will be these two, like basically characters are almost characters.
Right.
You know what is this relation here?
I only computed some small examples. They are certainly, yeah, they should behave like almost characters. They're not exactly irreducible characters or projectors.
They span the same function, the same space. They span. I don't know. Yeah, I certainly expect that, but I don't have a proof in the case of orthogonal symplectic groups. I think I have a proof in the case of linear dual pairs. The other thing is the local system on the torus, are they supposed to be tame? Because you didn't say that.
Oh yeah, yes, I forgot to say, but they are assumed to be tame. Yeah.
Okay, so Raphael had a question.
So you mentioned already, so the question of computing things. I mean, do you expect it to be possible to compute explicitly things without relying on the knowledge now of the correspondence? And if so, I mean, do you expect to be able to recover the classification, say, of unipotent cuspidal representations by using induction on dimension? I think it was kind of the original, one of the original aims in developing the Theta correspondence was to do something like that.
So what I can, so one thing that I think is possible is to give a direct description of these theta intertwining sheaves. So I can do it again, not in the symplectic orthogonal case, but for the linear case. I have a complete list of these sheaves, just in terms of more or less like Springer theory plus some kind of some analog Springer theory in this situation. So for symplectic orthogonal, it looks much harder, but I have some guess, but I don't know. I don't have enough evidence for it. So yeah. So what I can say now is that expect, independent of the construction that I gave here, there is a explicit description of these simple perverse sheaves, much as Lustig's description of character sheaves as you're using these explicit strata in the group and local systems.
Can I ask just a follow-up question? Can you work directly on the nilpotent cone in some way for the unipotent part or not?
Nilpotent cone,
I mean, or unipotent or the unipotent
for the group, or
I mean, if you, so this correspondence is compatible with the Lustig series. So I mean, you would expect the unipotent part to come maybe by Fourier transform or something like that, but to come from some correspondence that define some construction that takes place at the level of the unipotent variety, maybe.
Yes, I don't really understand the question.
No, maybe I'll ask. Maybe I can ask similar. So for character sheaf, there is one model where you can realize some linearized form, the sheaf on the Lie algebra, and they obtain a Fourier transform of some orbital things.
Yeah.
So, question: is there any analogous things here?
Not in an obvious way. So one feature that, so I should mention, our sheaves lives on this vector space, but this collection of sheaves is stable under Fourier transform. So it looks like it's somewhere between the orbital sheaves and their Fourier transforms. But it's not obtained by simply taking sheaves on orbits and Fourier transform.
Okay, so Tony had a question.
Yeah, so I guess the starting point was this multiplicity one property. And I usually think of that as fitting to a family of examples like coming from spherical varieties. I think your game kind of extends like to that situation.
I think the philosophy behind the construction is, it should generalize to somehow when you have, I haven't thought specifically about spherical varieties, but whenever you have this kind of multiplicity one situation where the space of intertwining operators has some explicit geometric model, then I think the similar, I mean, at least we should hope for such a geometric canonical basis to exist. But the starting point, like there's a moment cone or character sheaf case, G mod B, this will vary from situation to situation. But, the basic idea behind the construction is should generalize to other situations.
Mm-hmm. And can you just say a word about why the symplectic orthogonal case is harder than the unitary case?
The unitary case appears, so for the geometric theory of these sheaves, we can just work with the GL1, like linear pairs. That's much simpler because the Schrodinger model sees the full symmetry of GL1 times GL2. You don't need to change the model to analyze these sheaves. In a unitary case is you sort of add in Frobenius at the last moment. The classification of these sheaves, it doesn't see difference between unitary and GL. So for symplectic and orthogonal, then the main difficulty is that no Schrodinger model sees the full symmetry of the symplectic group. So yeah, that's
Thanks.
Are there further questions? Zhiwei, just very naively in terms of, so the theta correspondence, would it be crazy to think that you actually get functors between character sheaves for theta correspondent pairs?
I was about to say that. So yes, so just mention very briefly, there is a functor from theta sheaves to character sheaves on G1 times G2. This is as much as I can say right now. From a theta intertwining sheaf, you can produce a character sheaf, well, maybe a direct sum of them, on G1 times G2, which should be thought of as some kind of correspondence, not really a map, but correspondence between character sheaves on G1 and character sheaves on G2. But I don't know much about this map. This is certainly deserves further study.
Tiep also had a question.
Oh yeah, so in the linear case, do you think that the commutativity of the end of G1 census, I mean G1 cross G2 of the Weyl representation?
Sorry, can you say it again?
So do you have multiplicity 1 in the GL case?
No. Yeah, GL case is not. Yeah, the multiplicity 1 doesn't hold. But the geometry is much simpler. Although,
Yeah, my question is because in the GL case, of course, you don't have multiplicity 1. Yeah, and we can see it in many examples. So that's why I asked the question.
Yeah, so it's not the motivation that I said in the beginning doesn't seem to apply to this non-multiplicity 1 case. But if you this geometric construction, if you follow that in the GL times GL case, it still makes sense, and it gives a collection of simple perverse sheaves on B. And one can even describe them explicitly. I didn't have time to say, but that's the geometry there is much more clear than the symplectic orthogonal case.
So if there's no further questions, I don't see anyone's hand raised that. So thank you very much, Zhiwei. And we will reconvene in 20 minutes, I believe.